Hello everyone. So in this video we will solve closed loop transfer function for the first problem and loop gain transfer function in the second problem. So there can be many methods we can solve. We can use Miller approximation also. So I'll give only a hint for Miller approximation and you can do by your own. Okay, so here I'm assuming that channel length modulation is 0, so R naught will be infinite. Okay, so when we split feedback impedance, so that will come in the input as Z divided by 1 minus AV, and at the output it will come as Z divided by 1 minus 1 by AV. So without feedback resistance there will be infinite gain GM into R naught, that is infinite. So AV will be infinite, so that will at the input it will come as 0 and at the output it will come as RF. Okay, now from here what will be the output pole? Output pole will be 1 by Cp into RF. Okay, and what will be the gain? Low frequency small signal gain will be GM into RF. Okay, you can solve this. This is easy steps. And what will be the UGB? UGB will be gain into dominant pole location. So that is GM RF into 1 by Cp RF. So RF will cancel out and that will come as GM by Cp. Okay, so you can solve this and verify. Now we will use exact analysis. Okay, so let me copy this circuit. So for a small signal model, this is ideal current source, so this won't change. So that will be open circuit. Okay, and for low frequency small signal model, this capacitance will be open circuit. Okay, for DC it won't come in picture. Okay, now I will use a KCL here. You can use at output or input. So KCL at the input, we will get V in minus V naught divided by RF. So this current will be 0 and this current will be V in minus V naught divided by RF, and this current will flow through this GM V in. Okay, so that will be GM V in. If you want to include R naught, so you can also include here V naught by R naught. Okay, so I'm ignoring for now. So after solving this, we will get V in minus V naught equal to GM V in into RF. So this will come as V in 1 minus GM RF equal to V naught. So V naught by V in will be I'm taking out minus sign, so that will be GM RF minus 1. Now we got our DC gain. We don't call it DC gain, we call it as low frequency small signal gain. That is appropriate word to use. Okay, so AV 0 equal to magnitude will be GM RF minus 1. Now since we know that it's a one pole circuit, okay, so either we can calculate first pole and then UGB, or we can use UGB first and then pole secondly. Okay, so I will calculate UGB first. Okay, so to calculate UGB, our gain will be equal to 1. That means V naught equal to V in. Okay, So now what I'll do, I'll simply put here b not equal to b in. Okay, and then again I'll do the same calculation. Now what will be the here at now at UGB the capacitance CP will be in picture. Okay, so that won't be like open or short. Okay, so if we apply KCL here, so this current is 0 and V not equal to V in, so this current will also be 0. Okay, so now only KCL will be here on, that will be GM V in plus and this current through the capacitance, so that will be V naught divided by 1 by SCP equal to 0. Now V in, that will come as V not equal to this one is V in, so I will V in take out, so that will be GM plus 1 by SCP equal to 0. So V in can't be 0. Okay, so this term will be 0. So what will be the frequency? S equal to minus GM by CP, or omega equal to minus GM by CP. So this is our UGB frequency at which our gain will be unity. Now we will calculate pole locations. Okay, so for that we know that for a single pole system, our UGB is low frequency gain into omega p. So from here omega p will be UGB is GM by CP and gain is GM RF minus 1. Okay, so that will come as GM. So if I am ignoring this one term, so that will come as GM divided by GM CP into RF. So that will GM will cancel out and that will be RF into CP. So this is exact the same as we calculated from Miller approximation. Okay, so here UGB is GM by CP, gain is GM RF and pole is CP RF. What we see that here, what is different from that Miller approximation, when we draw Bode plot, so this is our pole location. So in exact analysis or Miller approximation, our unity gain frequency is same, that is GM by CP, and pole location is 1 by RF into CP, and this gain is GM RF minus 1. Okay, and this is ACL, frequency response omega. So here we can draw one result that our GM RF minus 1 must be greater than 1. This condition we were missing in Miller approximation. Okay, this should be greater than 0. From here GM RF should be greater than 1 and RF greater than 1 by GM. So this is the condition we were missing. So now this condition represents that RF must be greater than 1 by GM. Otherwise, if this value is less than 0, so that will, our gain will be negative and that will degenerate our circuit. Okay, so to get a gain, we must put our RF greater than 1 by GM. So when you design this circuit is you will use in bias to the another circuit. Okay, so you must put RF greater than 1 by GM. Okay, so I hope I was able to explain. Okay, first problem. So let me write the complete transfer function. So that will be AS. So that will be GM RF minus 1 divided by 1 plus S by omega P. So omega P is RF into Cp. So that is RF into Cp. So this is our transfer function. So now in second problem I will calculate loop gain. So what I will follow that procedure. You can follow the same procedure to calculate the loop gain in the first problem. Okay, and this closed loop transfer function is usually easy, so that you can calculate in second problem. So in second problem I will calculate only loop gain transfer function. So let me copy this circuit. So in this problem we have to calculate loop gain transfer function. Okay, so by saying this circuit we can say that RF is the feedback element. So this is taking output and fed to the input. Now we will draw loop gain model. Okay, so loop gain model will be different from closed loop model. Okay, and our open loop model. Now we will draw loop gain model. Okay, so while calculating loop gain, we break the loop at the any high impedance load, and then we apply a test voltage there, and we calculate the output voltage at the second terminal where we break the loop. Okay, so this is something high impedance node, so we will break loop here. Okay, so now that will be look like this is our minus GM, and this is R naught, this is Cp. Okay, and here I broke the loop, and I will apply a test voltage, and I will measure the output voltage at the other terminal. So this is the other terminal, and this is our blocking capacitance Cb, and this is our input. Okay, now how we can calculate like exact analysis, and we can calculate loop gain will be Vf by Vt. Okay, so while calculating exact analysis, suppose I am saying this one V naught dash. So what will be the Vf? So Vf will be, so I will ground this input. Okay, and we break the loop. Okay, so this is input is 0. So Vf will be simply a KVL. So that will be 1 by SCB divided by RF plus 1 by SCB. So that will come as 1 plus S RF CB into V naught dash. Okay, now we got this equation, and we will write one equation here, KCL at the output. So we will get second equation, and after solving both equation we can get our Vf by Vt. Okay, but that approach will be like lengthy, and we won't get any insight of the circuit, so we will use some approximations. Okay, so we will use the first approximation as Cb is greater than parasitic capacitance. Okay, so I will use approximations as Cb is greater than Cp. So we know that Xc is 1 by omega c. So in my last video I also explained that Cb will short first. Okay, and then CP will short. Okay, so how we can solve this circuit? So first we will calculate pole due to CB. So we know that if we are calculating pole due to CB and CB is existing in the circuit, so at that time our CP will be open circuited. Okay, so I will draw again that loop gain model. So this is minus GM and this is R naught. Our parasitic capacitance is open circuit, and I have broke the loop, and this is our test voltage Vt, and this is Rf, and this is our V, and this is our Cb. So pole due to Cb, what will be the pole due to Cb? That will be omega p equal to 1 by Cb into Rth, looking from Cb. So now this is the model of the loop gain. Now to calculate Rth, we know that to calculate Rth, we put V in. This is already 0 in loop gain model. Okay, so we put our input is 0. In this model, input is test voltage. So that will be Vt equal to 0. So this Gm Vt will be also 0, means this won't deliver any current. Okay, now if you look from this side, what we will see? We will see only Rf plus R naught. Okay, so this V in 0 in loop gain model, we again put 0 Vt to calculate Rth. Okay, so now what will be the Rth? Rth will be Rf plus R naught. Both are in series. Okay, so what will be the omega p? Omega p1 will be 1 by Cb into Rf plus R naught. Okay. Again, if we say that R naught is usually greater than like Rf, so R naught if greater than Rf, so that will be omega p1 will be 1 by Cb into R naught or G naught by Cb. Now we will calculate pole due to Cp. Now pole due to Cp. So since Cb is large, so that will be treated as a now short circuit. Okay, and Cp will exist in the circuit. So now if I again draw the small model for loop gain, so that will be minus Gm. This is R naught, and this is our test voltage, and this is Rf, and this is behave, and be in 0. So this is our loop gain model. Now we know that Cb will be short circuited, so Cb will be infinite. You can say our xCb equal to 0. Okay, and now to calculate Rth, looking from this Cp, to calculate Rth, again we put our input 0, so that we will put this Vt 0, so this current will be 0. Now if you look from this side, now in this case R0 and Rf is in parallel. Okay, so now in this case Rth equal to Rf parallel R0. So we have taken one assumption that R0 is greater than Rf. Okay, so in this case what will be the total output? So that will be equal to Rf. Okay, so whole impedance looking from here will be Rf only. Now what will be the pole? Pole will be omega p2 equal to 1 by parasitic capacitance into feedback resistor. Okay, now we got our both pole. Till now we haven't calculated our DC loop gain. So again, now let calculate DC loop gain. Don't call it like DC, we will call it like small signal low frequency loop gain. Okay, so again let me draw that model. So that is minus GM, this is R naught, and this is our CB, this is RF, this is our test voltage. Okay, this is VF, and this is input. Now what will be the low frequency gain? So in this in low frequency, both capacitance will be open circuit. So I will open, and I am measuring output here. In this case, this input is 0. So loop gain DC will be 0, will be VF by Vt. So this current is minus Gm by Vt. Now this current will be divided in both resistance. Since this is open circuit, so there won't be any current here. So this current is 0. Okay, so whole current will flowing through the R naught only. So and this VF will be this VF only. Since there is no current flowing through RF, this current will be 0, so no drop across RF. So this VF will be this VF only. So VF by what will be the VF? VF will be minus GM Vt into resistance R naught. So from here VF by Vt equal to minus Gm R naught or minus Gm by G naught. Okay, so now the complete transfer function will be loop gain transfer function will be loop gain for small frequency, and then 1 plus S by omega P1 and 1 plus S by omega P2. So this is minus Gm by G naught. Okay, so I am taking magnitude only. Okay, I am plotting magnitude. So this is Gm by G naught, and first pole location is due to CB, and that is G naught by CB. Okay, G naught by CB, and second pole is CP 1 by CP into RF, 1 by CP into RF. So that will be Gm by G naught divided by 1 plus S into CB by G naught and 1 plus S into CP into RF. So this is our complete loop gain transfer function. Okay, so this is how we can calculate. So and after approximation we got this expression. So if you want to recall, and suppose we got this expression by any condition, so what will be the final condition? So we had taken one condition that CB greater than CP and RF is less than R naught. So you can multiply, you can tweak this both condition and you can get a condition. Okay, so suppose I am multiplying CP in this equation. Okay, so I am multiplying CP, so that will be CP RF greater than R naught into CP. Now CP, so what will be the G naught by CP? So that will be less than 1 by CP into RF. So along with you can also multiply CB and you can get one condition. So at this condition we are getting this loop gain transfer function. Okay, so I hope I was able to explain. Okay, so you can now calculate loop gain of this. Okay, and closed loop gain of second problem. So again, let me summarize what I did. I break the loop at a high impedance node, and then I will apply a test voltage at one node, and I'll measure output at the second broken node. Okay, so I model the circuit like this, and in loop gain I put my input at 0 and I apply test voltage. I will calculate Vf here. Okay, exact analysis will be lengthy and we won't get any insights. So I will assume that CB is greater than actually CB blocking capacitors are very much larger than parasitic capacitance. So now I will calculate RTH in this loop gain model. So Vin was already 0 in loop gain model. Now this test voltage will be 0 to calculate our RTH. So in this case RTH is simply in series with RF plus R0, and in second case it will be RF parallel R0. So after that we calculated our DC low frequency small signal gain. Okay, so Vin was already 0 in loop gain model. I applied a test voltage, I calculated output voltage the other side, and I got Gm by G0, and finally I put all the parameters in this transfer function. So this is my loop gain transfer function. Okay, so please let me know if you find any wrong analysis or you didn't understand. Okay, bye, thank you.